Now we're going to be going a little bit more technical and diving deeper with Howard Wu from Blockchain at Berkeley and SCIPR. What's the? SCIPR Lab, sorry. And we're really excited to see what you have to say. But I think, just so you guys know on this room, we're going to be getting like deeper and deeper and deeper into zero-knowledge proofs. I think if you at some point find this gets a little too technical, there's some other things going on. And we have the plan. Cool.
Awesome. My name is Howard, and today I'm going to be talking about, first an introduction building on top of Jack's last talk on zero-knowledge proofs, and in particular we'll look into one specific type. It's a class of proofs called zkSNARKs, and lastly we'll talk about a library, Lib SNARK, that implements these zero-knowledge proof systems and is used in a lot of deployments in industry today. So from a very high level, cryptography is powerful because it's useful for building secure systems. And historically speaking, a lot of the cryptography work is used to provide these security properties for data. If you think about information, when you transmit it, if you want confidentiality, you can encrypt your information and send it. Additionally, if you want to have authenticity about the information you receive, it makes sense to have like a checksum, a signature, something that allows you to verify and validate that the information indeed is the correct one. But what about security properties for computation? This is an area that is very useful because as machines become more powerful and everyone is now living in this digital era, being able to communicate and execute protocols together is extremely valuable. And providing security guarantees on the integrity of computations is extremely useful. So cryptographic proofs offer these privacy-preserving integrity for computation. And when it comes to cryptographic proofs, it's a powerful defense mechanism that it enforces that malicious actors can be caught. And what makes that extremely useful is in the case of blockchains. In the case of decentralized protocols, where there is a model that users are mutually distrusting, it's a very ideal situation to have proofs about your claims, about what you've done, and to enforce the protocol's correct execution. Cryptographic proofs bridge together multiple disciplines. This spans anywhere from mathematics to complexity theory to cryptography to security. And these are all areas where there's a notion, this formalization of proofs. You can think about from the mathematical standpoint that a lot of mathematics is reasoning on formal proofs. And computer science has come to reinvent it with things like zero-knowledge proofs. If we look back at some earlier models and earlier work of cryptographic proofs, you can think about a lot of like multi-party computations where there is this notion of a private input from different users. And these inputs designated in red, x1 through xn, could potentially be, say, bank account balances. Perhaps the problem, the function f, is to say who is the richest of, or the wealthiest of all of the n participants. And certainly, people don't want to disclose what their net worth is, but perhaps within this group, it's desirable to figure out who is the wealthiest of that subset. And in this case, potentially the output could be the user who has like the most wealth but does not disclose the amount. And in these types of situations where there is a notion of privacy, it makes a lot of sense to have a computation where people can have integrity, namely that in executing this protocol, they aren't able to lie about their wealth, they aren't able to lie about their statement, and they also can compute this in a fair fashion. But if you look at these early constructions, these systems were very different from what some of the stuff we see today. They're closed networks. We're talking about participants who have to a priori know what the sample set is going to be, and they have to all be online and available to talk to each other. Because of the communication costs involved, this results in a lot of scalability issues, and so oftentimes these problems are reasoned about in a small setting in a small domain. But in these cases, things like zero-knowledge proofs, which we'll formalize in a second, allows you to ensure that every message is sent according to this protocol, that no single user is trying to cheat their way out of that function. Fast forward to today, and you have things like blockchains, where it's a very different world. These are environments that are extremely open. They are ones where anyone can join, and the participants can be online, they can be offline, they could be on for 1 minute and then disappear and then come back on. It's very hard to say, and additionally, this is at a planetary scale. And so these environments are very well motivated for things like cryptographic proofs. It ensures a few things. For one, like if you have a proof that you wanted to make a claim about in this case, one, you would want it to be succinct, meaning that this is a proof that's very small, it's very efficient to check, and it's something that can actually live and be posted on a ledger. Additionally, non-interactivity is a desirable property, meaning that if I'm to post a proof online, then I don't actually have to enforce that the prover remains online and have this channel with them to do some type of interaction. It's better that they can post a proof, go away, and for the rest of eternity, anyone in the system can go and check this proof. Additionally, you'd like it to be publicly verifiable. This is especially desirable in things like blockchains. And lastly, because of the public nature of these chains, zero knowledge is a valuable component to say that certain inputs may not want to be revealed. So to start from the ground up, there was this notion of zero-knowledge proofs introduced by Goldwasser, Macaulay, and Rakoff. And in this setting, these are privacy-preserving cryptographic proofs of computational integrity. You can think about this as two parties, a prover and a verifier. The prover says, hey, I know some x such that the claimed output y is equal to this function applied on my private input. And this notion is something that is a valuable information for the verifier to check. The verifier wants to know, hey, do you really have knowledge about this claimed output? Do you have the private input that gets you to this claimed output? And so the prover has this notion of knowing a function, a claimed output, and some claimed input. The verifier only knows the function and the claimed output, and is reasoning through this interactive protocol to determine whether the prover indeed knows some private input. What this construction gives you, for one, is completeness, which is to say, loosely, that an honest prover will always be able to convince a verifier of the correctness. Soundness, in this case, says that a malicious prover should not be able to convince a verifier of this claim. And lastly, zero knowledge, which is to say that it should not reveal any information. The formalization here uses a simulator, and this is to say that there should be some type of indistinguishability, and that component is what's so valuable in saying that zero knowledge, it means that I don't reveal any information about my original inputs. So this is a very powerful cryptographic tool. However, this early construction has a lot of downsides to it. First off, it's an interactive protocol, meaning that the prover and the verifier have to be online and they have to go back and forth and chat with each other. Additionally, it's not succinct. What this means is that the verification, the communication complexity is on the order of the time it takes to compute the function itself. So if I'm in the setting of saying, I have maybe like a 1 petabyte database of health records, and I would like to find any people who are over 50 and have heart disease. That computation I could run on my local machine, but one valuable thing here is to say I want to outsource it to a cloud provider to go and make this computation. And doing so would be something where I don't know if they really ran it on the whole petabyte. Maybe they just do the first terabyte, find 20 results, and say, hey, this is all I got. Well, in that case, there's no way for me to check unless there is a proof involved. And a zero-knowledge proof is a valuable way to demonstrate this. However, if it takes as long to run that computation as it does to check the actual integrity, then I have gained no advantages in this case. And so succinctness is a very desirable property. Lastly, there is poor concrete efficiency in this case. So this early zero-knowledge proof construction uses these things called probabilistically checkable proofs, or PCPs for short. And the idea about this is that you can pick some points and basically get a very high probability bound on the actual correctness. So, cryptographers don't sit in their offices and do nothing all day. They went straight to work on this and started looking at different ways to improve on the zero-knowledge proof. And one of the earliest works was in providing succinctness. This was work where they basically took probabilistically checkable proofs and lifted it to provide succinctness as a part of the protocol. What this enforces is, well, you have your original 3 properties, completeness, soundness, and zero knowledge, but now you also have succinctness, which is to say that the verifier can actually check this proof in a time that's proportional to the size of the function plus the size of the claimed output, not so much the runtime of the function itself. And obviously, this is a more powerful cryptographic primitive now. It's something that becomes more useful. It can be valuable in many domains, but it still suffers from 2 main problems. The first of which is interactivity. We still have to communicate back and forth, prover and verifier. It's not the most scalable approach. But additionally, it still remains very slow. So there was some work that was done by Silvio Micali. This was in 1994. This work was published. And it provided the first quote-unquote zkSNARK. It was a privacy-preserving cryptographic succinct non-interactive proof of computational integrity. And what he used was, in essence, a random oracle. You can think of this like a hash function, where you give it some input and the output should be indistinguishable from a random string. And using this to lift the construction allows you to actually create non-interactivity. This is, for formalities, a fiat-Shamir transform. And this construction is, in essence, the first zkSNARK. It is a zero-knowledge, succinct, non-interactive argument of knowledge. Zero knowledge, as before, proofs should not reveal anything about the witness, that is your private input. And it should be succinct, meaning that they should be short, the proof itself should be short, and the verification should be fast. It should be a non-interactive protocol, so there should not be a necessity for interaction between the prover and the verifier. And lastly, it is an argument. So here, in essence, the difference between a proof and an argument is that your soundness holds only up to computational bounds, but having a computationally bounded verifier in this case provides you a zkSNARK. So this is a much more powerful cryptographic primitive, and as we have resolved the interactivity problem. But as you see, this is still a use case that is built on PCPs and has costs with respect to the concrete efficiency. So for about a good 10 years, there wasn't so much work that was done in this area, and a lot of people had gone away and done other things, and eventually there was a study into these strong assumptions that were made, and there have been multiple approaches in trying to tackle this construction that uses PCPs. So zkSNARKs without random oracles is a desirable property in this case, and early work has grown into a large bucket of work. Since the 2010s, we've seen a lot of developments in the research side of things with these constructions that are still based on PCPs, but use much different assumptions than before. And these remain rather impractical to this day. But there's another class where the constructions are based on linear PCPs. And these things are actually very, very practical. They use pre-processing, so there is a cost involved, and the architecture is different, but it is very practical for actual use cases, actual deployments. And for this reason, Lib SNARK was born. It was a library that includes the implementation of many different like zkSNARK protocols, and these are all publicly available for anyone to use and test and benchmark and compare and study. So let's describe what pre-processing means here. Pre-processing means that there has to be some setup phase. A setup phase is one where there is a delegated control to basically generate some common reference string. In this case, there are 2 pieces to it. One is a proving key, and the other is a verification key. The setup is ran by sampling some randomness and constructing these keys. They're then broadcast out into the world. It's a one-time thing that becomes available for anyone to use. Then for anyone who wants to try to make some claim about some statement relevant to this problem that's been set up, they can act as a prover, provide their claimed input, and put the claimed output out, and run this to generate a proof. This proof is broadcasted out to a network. It can be to a verifier, it can be to a blockchain, it can be anywhere. And the verifier will take this proof, it'll query it, and check very efficiently whether the prover actually knows something. In practice, we see that these constructions are rather efficient now, with the prover costs at about 0.05 milliseconds per gate. The proof is also very succinct. It's 128 bytes, 3 group elements, and it's very fast for a verifier to check. We're talking about 3 pairings, which costs about 3 milliseconds, and a linear number of exponentiations at about 0.4 microseconds per byte. This particular construction is one that we have in Lib SNARK that can be accessed at that URL. But there are still open problems and open developments on this front. For one, there's this notion of a trusted setup. So in cryptography, having a setup phase is not so much of an issue. We are talking about theoretical constructions, but in the real world, someone has to go and run this setup. And this is a point of contention in a lot of blockchain architectures that use zkSNARKs. So having a trusted setup is a potential issue, and there has been active developments on this front. On the second hand, there is the prover is bounded because of memory-intensive computations, and memory-intensive computations is something that only the prover has to reason about, but nevertheless must deal with. And so there is also active work in this area that I'll talk about in a second on how to resolve these. And lastly, malleability. That if a verifier were to receive a proof, how can he or she believe that this proof is indeed the corresponding and correct one? And this is an area where it's like, you can think about it from a man-in-the-middle attack perspective, that you want to believe that this proof is indeed the one that's been claimed. So on each of these fronts, we see multiple developments. First, there's been work by BCGTV15 and also BGM17 for multi-party computations. These are scalable MPC protocols to actually distribute and delegate the construction of this trusted setup. And you see this with work from Zcash, for example, where they're currently doing their powers of tau computations. And it's something where any individual can participate in. Anyone who has a distrust of the actual common setup for everyone to use can proceed to participate in this MPC protocol, and so long as they themselves are honest to themselves and generate a result that is included in this final output, they can believe that that whole process has not been corrupted. So long as one person in the entire MPC protocol is honest, the entire process has been fair. And so this is one way for anyone who has doubts to basically believe, because they must believe themselves in the process. In the second hand, there is distributed zkSNARKs. This is an area of research work that I spent the past year on. And in essence, what it says is, look, computing these things is very memory intensive. What if you could, in essence, distribute the computation process across a cluster of nodes? So say you have like EC2, or you have like Google Cloud or Microsoft Azure. You can spin up a large set of nodes, and what we have done is basically distributed the algorithms such that they're not bound by a single person, and they're not bound by a single machine, so that you can expand this and just throw more cores and throw more memory, and therefore scale almost infinitely. From our initial benchmarks, we had seen that, well, first off, Lib SNARK is the state-of-the-art implementation at around 30 million gates. That's where it roughly caps off at. And what we have been able to demonstrate is that this scales to the billions of gates now. So this becomes very practical for a lot of large problems, so long as you're willing to pay the compute costs and the time to do it. Lastly, in terms of addressing the issue of malleability, there was a work last year by Groth and Mahler, GM17. This protocol is a simulation extractable zkSNARK, and the cost to actually construct this proof is about 20 to 30% more than Groth 16, which was the efficient construction you saw before. But in doing so, you actually get this protection from man-in-the-middle attacks as part of the properties. So we had just talked about this particular pre-processing zkSNARK, and if you look at the details, this is actually a specific type of pre-processing zkSNARK. It's a pairing-based pre-processing zkSNARK. The reason is that this is using pairings in order to do this check. And to go into some details on this, we can think about this as a prime order bilinear map. So a pairing, in essence, has 3 finite cyclic groups of prime order P. Call it G1, G2, and GT. And the idea is that you will have some type of a mapping, an efficient mapping, that takes as input an element from G1, an element from G2, and it gets you an output that's an element in the group GT. So given some element G1, G in G1, some element H in G2, a bilinear map preserves bilinearity, which is to say that this function mapping of G to the A and H to the B should be equivalent to the mapping of G and H exponentiated to AB. And for notation, I will just use A bracket 1, B bracket 2, and C bracket T, and that's to say A is some element that lies in G1, B is some element that lies in G2, and C is some element that lies in GT. So going back, we had this pairing-based preprocessing zkSNARK, and this in particular is the Groth16 protocol. If you want to study this, there is a lot of research and literature out there to deep dive, to give a very high-level overview and to give you a notion about what a zkSNARK really looks like underneath. I will walk you through what the underlying equations are. By no means is this something that you must digest immediately. There's a lot of algorithms underneath that form its construction, and this is more for your knowledge to see and to get a reason about, to get some intuition on how a SNARK works. So initially, in the setup phase, the setup generates some common reference string. I'll call it sigma 1 and sigma 2. And you can think of these as like vectors of information. It's just these generated random values that are valuable for actually constructing the system and for running and playing this prover-verifier game. So in this case, you have the proving key and the verification key. You can see that the proving key contains much more information than the verification key, and it's a much larger problem. In fact, the proving key is typically on the order of the problem itself, and the verification key is independent of that. Once you get these random values out, this is a one-time operation that is put out in the public. Then participants who want to make some claim of knowing some private inputs can run an algorithm. They're running this computation to demonstrate their knowledge. So in this case, you have three equations, A, B, and C. And these are used to construct what is called, in essence, a Rankine constraint system that's mapped into these quadratic arithmetic polynomials. And this use case allows you to generate three concise group elements, namely A, B, and C. So A and C lie in G1, B lies in G2. And that is the proof. It is three group elements. Lastly, the verifier, upon receiving this proof, looks at its common public knowledge, the verification key, and takes the proof in and says, hey, let me do this check. If I have A and B and I do a bilinear map on this, that expected output doesn't match the right-hand side, which is alpha beta times this polynomial and C and delta. And that value is, in essence, the fundamental check to say, look, does this equation match? Does it make sense? And does the prover really know what he or she is claiming? So to give some discussions on efficiency, this is a very efficient construction, much more efficient than the earlier work that you saw in the 80s and the 90s that we discussed. The proof size, as we said, was three group elements, two elements from G1, one element from G2. And the prover is also relatively quick. There is m plus 3n exponentiations in G1, and there is n exponentiations in G2. And the verifier handles a linear number of exponentiations in G1 and also three pairings. So this work has been integrated into a library called Lib SNARK. It's a C++ library that implements a lot of these zero-knowledge proof systems. And Lib SNARK is quite a behemoth. At its base, we have this algebraic core, which includes multiple things. First off, there is libff, which is a C++ library for finite fields and elliptic curves. This library implements finite field arithmetic, bilinear group arithmetic, and fixed and variable-based multi-exponentiation. This was something that is incorporated into a lot of projects independent of zkSNARKs, and it's very useful as a library for people to just develop and do algebraic constructions on. Next, we have the second layer, which is polynomial interpolation, evaluation, fast-forward transforms, and finite fields, and Lagrange coefficient computations. These things are all encapsulated into a library called libfqfft. It's a C++ library for fast-forward transforms in finite fields. I'll say this is an area that is relatively understudied. Fast-forward transforms have been well studied, but in the domain of finite fields, not so much. We only have so much knowledge about the constructions, and you'll see a little discussion about them shortly. So on top of that, we have a backend. The backend is comprised of multiple components. First off, you can think about arithmetic circuits, Boolean circuits, proof-carrying data. These are basically the models that say, how do I represent a notion of a statement? How do I represent a notion of a problem? How do I actually reason about something that I would like to prove? And these are the representation of those statements. On top of that, there is a front-end interface, which includes multiple things. This is a small subset of it, which is like there are things like zero cache, there are things like tinyRAM, there are things, a general library in here that is for gadgets and protoboards, and what that allows you to do is, in essence, create your own gadgets, your own representations of these problems, and provide a very easy interface to construct these circuits that allow you to actually reason for a proof on. And on the application layer, well, there are a whole variety of different applications. Certainly, zero cache has been extended out to a project called zcash, I'm sure you're familiar with. And there's also other areas where there's privacy-preserving micropayments, privacy-preserving computations, and also from Jacob, this library called Socrates. It's a toolbox for zkSNARKs on Ethereum, and it allows anyone to, in essence, make some claim. For example, like the crossword puzzle that Jack had mentioned, where in essence, if you know the answer, you can construct a proof, and potentially maybe if you know the answer but don't want to reveal it, or in the case of Ethereum, it's not practical to reveal the answer because then anyone can game the system. You can have a smart contract that runs a verifier and checks your proof to say, hey, do you actually know the answer? And if you do, maybe it pays you out some reward. This is a very useful construction, and this library, I believe Jacob will be talking about soon. So for anyone who is interested to develop on Lib SNARK, there are a lot of different choices that can be made in your construction. At its core, we have libFF, which provides these elliptic curve implementations. There's the Pareto-Nerig curve, Edwards curve, MNT4, and MNT6, and these are all at varying bits of security. There are open fronts for us to explore and add on new curves, and for anyone that's interested, please contribute. These things are very useful for a lot of the bilinear group arithmetic and the bilinear group constructions that I had discussed earlier. Additionally, we have libFQFT, which provides a set of 5 evaluation domains. So you have a standard radix 2, an extended radix 2, a step radix 2, a geometric sequence, and arithmetic sequence. So for these problems, with most cases, you can find a lot of roots of unity, and that allows you to reason about things for FFTs very quickly. But in the case of finite fields, depending on your modulus and how your field looks and is constructed, you may not have sufficient numbers of roots of unity for what you want. And that's where we provide things like the geometric sequence and arithmetic sequence for computing those. But the performance costs on those is much, much slower. And if you go to the GitHub page for libFQFT, on the README, you can see the performances. We've benchmarked the implementations of these across multiple domains on all of these evaluation domains. This stuff is useful for things like polynomial interpolation and evaluation. So going one layer above, we have the arithmetic circuits. And at its core, an arithmetic circuit looks something like this. You have some inputs like A1 and A3. And perhaps in this case, the quadratic equation is checking. Does A1 plus A3 multiplied by A3 equal this value at A2? And this, in its most general form, can be expressed as this combination of terms. The summation of A sub I times U sub I, multiplied by the summation of A sub I V sub I, and you check if this equals the summation of A sub I W sub I over the variables A from 1 through M. And for convention, we always keep A sub 0 to be the one value. So an arithmetic circuit can define an MP language with statements that are encoded in A1 through AL. And the witnesses, meaning your private inputs, are stored in AL plus 1 through M. So to build these arithmetic circuits, if it's a very simple problem, you can imagine that it's rather efficient, rather quick, and it's a small problem. You can just kind of write it in one file and do it and move on. But in practice, most people like to reason about real problems like that are much larger. And in order to do that, having it in one file, just like with these constructions, is quite a mess. And so in Lib SNARK, we introduced this concept of a gadget. A gadget, in essence is a collection of some arithmetic circuits, some representation of a problem. It can be a subproblem. For example, if I wanted to do a hash function of a hash function of a hash function, like I hash some value 3 times, it doesn't make sense for me to like write an arithmetic circuit that's like I put the inputs into that directly 3 times. Rather, it makes sense for me to encode the hash function itself as a gadget, and I call that gadget 3 times so that it becomes an independent and easily debuggable form. So in Lib SNARK, we provide 2 libraries, gadget lib 1 and gadget lib 2. These are low-level libraries that expose all the features of the preprocessing zkSNARK. And in our case, we provide a lot of boilerplate gadgets for free. There is finite fields, elliptic curves, pairings, multi-exponentiation, hash functions, Merkle trees, CPU checkers, and even zkSNARK verifiers. The zkSNARK verifier is useful for some cases like recursive SNARK composition, if you're familiar with it. And these are all things that we provide immediately, but the library also includes these protoboards that allow anyone to build out any type of gadgets that they would like, as long as it can be expressed, which it can be in arithmetic circuit form. The underlying constructions use different types of representations, the most common being a rank 1 constraint system. So that's an overview of Lib SNARK. There are so many pieces involved in it, and in our case, this has been a very large engineering effort that has also been helped by a lot of developers that are building applications using zkSNARKs, and also by people who are interested in this field. For any of you that are interested in developing on it, I've set up a repo at github.com/hardwoo/libsnark-tutorial. And what this provides is an immediate developer environment for you to just git clone and start working on. It, in essence, provides all the install scripts for you to install Lib SNARK on your machine. Current support is mainly on the Ubuntu side of things, but once you get that up and running, you can immediately start importing gadgets, constructing them to solve some very basic problems, and it's meant to be a tutorial to make you comfortable on the developer side. I get a lot of emails with respect to like compilation, and so this library is meant to resolve half of those things and to make it easier for people to actually develop zkSNARK applications. For anyone who is very familiar or would like to get more involved on the development side, Lib SNARK remains an open library that is out for anyone to help contribute to. We have a host of different things we would like to upgrade and update in here, namely, for example, with respect to the curves that we provide. BLS 12381, the curve that Zcash is using, is something that would be very desirable for us to include in Lib SNARK. And there are other areas where we'd like to refactor out certain libraries that have grown to be much larger than we had anticipated. And there's a lot of areas that you can get involved in. If you'd like, there's a Google form at this link, libsnark.org/getinvolved, and please be in touch. But other than that, I want to say thanks, and I hope this was informative. I'm happy to answer any questions outside after this. Yep. Thanks.
All right, any questions?
Hey, thanks for the talk. I was wondering if there's been any research done on how the implementations are resistant to side channels. So, for example, if an attacker could observe or infer the amount of time it takes for a prover to produce a proof, that might reveal something about the inputs.
Yeah, side channel attacks are a very real problem, and at least in this case, I'm not so familiar on that body of literature, but it's an area that I think is much more lower level in terms of the actual CPU level of running these computations. Side channel attacks are very prevalent.
Any other questions? I have one. When I talk to people about Zcash and zkSNARKs and things in general, I get a lot of comments that, this is very new cryptography. Can we really trust it? Does it really work? And we're not really sure. What would your response to that be?
Yeah, I would say first off, I think a lot of this stuff, like as people call it, is like spooky moon math. And overall, look, like these are very formal academic works. These are peer-reviewed papers that have very complex constructions, but have been reasoned through by academics in this space. And in terms of the actual proofs themselves, they demonstrate perfect completeness and perfect zero knowledge. That means that if someone really knows this information, they can, with complete assurance, actually enforce the correctness and convince a verifier of their claim. And additionally, they can ensure that they don't reveal any information about it. So having that as like a principle is extremely valuable. And I think that some of the concerns that are in this space have to do with the practicalities of it, the engineering side of it, where indeed, there is a notion of a trusted setup. And this is an area that I think the current innovations that have been happening in the academic world are resolving these issues. Providing some type of MPC protocol is useful, but I would also say there's new developments on the area of SNARKs where there is no notion of a setup here. And as those things become more practical and come online, I think that there will be much more choices for the community to reason about.
All right. Thank you very much.
Yeah, awesome. Thank you.